Okay, so let's look at another example. So this is Q, say it's the state here. The two ends are must and also. At the end of the translation, we have words 1, 2, 3 translated, the other ones aren't. We have the position of the last endpoint of the last phrase is 3, and then minus 2.5. So PHQ is again going to be a set of possible phrases which can follow this state. And so let's see. So we've translated words 1, 2, 3. So natural things here would be things like 4, 5, this criticism. Okay, because this phrase certainly doesn't overlap with this bit string, and in addition 4 is close enough to 3 that this is allowed. Or we could have 6, 6 seriously. Again, there's no overlap in the bit string, and 6 is close enough to 3 that there's no violation. We might even have 7, 7 take. Again, there's no overlap in the bit string, and we can verify 3 plus 1 minus 7 is equal to the magnitude of minus 3. It's less than equal to 4. That's fine, assuming the distortion limit is again 4. And so on and so on. So there's going to be a whole set of possible phrases. And notice that just by looking at the state, we can calculate which phrases can actually follow it. Another very useful definition is going to be the following. So for any Q and for any phrase P, I'm going to define next of Q and P to be the state formed by combining state Q with phrase P. So what does that mean? So let's say we take Q here, and we take one of these phrases, for example, 7, 7 take. Okay, so this is going to return a new state which is formed by basically concatenating this phrase on the end of this state I've shown you here. So the state in this case would be also take, because those would be the last two words in the translation. We would have the following 1, 2, 3, and then take is in position 1, 2, 3, 4, 5, 6, 7, and so now we update the 7th bit to reflect that. It's a 1. We record the endpoint of this phrase, 7, and we update the score. So this would be minus 4.9 or something, where this is again calculated using a combination of the trigram language parameters, the phrase score, and the distortion score. Okay, so this is basically just implementing the graph definition I showed you earlier. So we have this transition, 7, 7 take, with this particular phrase. So this is just exactly what I've shown you here. So here are the formal details of how we actually define this next function. I'll just go over this quickly because I think you've gotten the intuition from the last slide. So the next function takes in a state Q and a phrase P. So the state Q consists of E1, E2, bitstring B, a position R, and a score alpha. And the phrase consists of a start point and end point and a sequence of capital M words. We'll call this epsilon 1 through epsilon M. Then this next state is the state Q primed with new elements, E1 primed, E2 primed, B primed, R primed, alpha primed. These are calculated as follows. So let me just briefly give a sketch here. E1 primed is E epsilon capital M minus 1. E2 primed is epsilon M, so we just take the last two words in this phrase. And we've got to be slightly careful about the case where this phrase is just one word long. These definitions capture that. And then we update the bit string, so we say the new bit string has values 1 for any I in the range S to T. So these are the start and end point of the phrase. Otherwise, we just copy across the bit string from the previous bit string. We define the endpoint, R prime, to be the endpoint of this new phrase. That's T. So R primed is T. And then alpha primed, the score for the new state, is going to be alpha, the score for the old state, plus the score of the phrase, G of P. And then we have some language model scores. These are trigram language model scores. And then we have a distortion parameter, and then we have a distortion cost. Notice that we have R, the endpoint of the last phrase. We have S, the start point of this new phrase. And we can calculate this distortion cost in a very straightforward manner from that. Okay, so that's a formal definition of the next function. We're almost there in terms of defining beam search, but here's one more definition which will be very useful. It's a very simple function which just returns true or false, depending on whether two states q and q primed are equal under a particular definition of equality. So say I have two states, q and q primed. The equal function is going to return true if E1 is equal to E1 primed, E2 is equal to E2 primed, B is equal to B primed, and R is equal to R primed. So it's actually going to ignore the scores, and it's just going to take into account these four examples, and it's going to return true only if these four things are equal. We'll see soon why this definition is important, and why in particular we don't check the alpha and alpha prime scores. Okay, so we may have, for example, two different ways of reaching a particular setting. So say we must also, maybe it's something like this, and maybe we have another state which looks like this. So it actually has the same components for these first few entries, but has a different score. So they say this is Q and this is Q primed. In this case, EQ of Q and Q primed is equal to true.